All right, so you're here maybe because you're trying to do some redox stuff and you're struggling with it a little bit, okay? So what we're going to focus on first is assign oxidation numbers, which is fundamental skill. We have to be able to do that before we can then start writing our half reactions of oxidation and reduction. So what we'll do first, we'll just look at a couple of compounds. I figure out how we can identify what the oxidation numbers are for all the elements in the compound. Once we've built that skill, we'll move on to some natural reactions. Okay? So let's delve in. Let's do this. All right. So we're going to start with carbonic acid here. So or hydrogen carbonate. Okay. What we have is two hydrogens, a carbon and an oxygen. Now there are some rules, right? So hopefully you've already got in your notes somewhere some rules about how we can use the easy to identify or easy to assign oxidation numbers to then figure out those that are maybe not so easy. All right, so here's a few of the rules. Elemental form, right? So if I have oxygen gas, so oxygen is not attached to anything. If I have hydrogen gas, or if I have just zinc metal, for example, those would all be elemental forms, and we're going to assign those a 0 for their oxidation number, right? Now, if we're talking about a compound of some sort, a couple usual gimmies, usually, all right, are oxygen, which is nearly always going to be a -2, and hydrogen, which is nearly always going to be a +1. There are exceptions. I'm not going to get into those right at the moment, but those are kind of our gimmies, and then we can often use those to then calculate what we don't know already. All right, so let's go. Let's do this. I've got carbonic acid or hydrogen carbonate, however you want to say that. All right, so what are my gimmies in this compound? I know that oxygen's a -2. I know that hydrogen is probably going to be a +1, right? Neither of those is an exception to that. Okay, so what we have to do with that then is we have to look at this compound in its entirety. Now, in chemistry, if this entire compound had an actual charge, all right, let me say the oxygen there is -2, right? There'd be a little charge up there, like you see in this zinc hydroxide, goofy little obscure molecule here, right? See how that has a 2- there? That's telling me that this whole thing has a charge of -2. There is no associated charge here. So what I'm going to do here is I'm going to set all the oxidation numbers equal to 0 in this case. All right? Now, when I do that, I have to also account for the subscript. All right? So with my hydrogens here, for example, I have two hydrogens, each at a +1. I'm going to say 2 times 1 plus. Okay, I have one carbon, 1 times x. Okay, plus, I'm going to give myself a extra space, 3 times -2 equals 0. All right, so again, let's just stop for a second. Let's talk about what I just did, right? So I made this into an algebra equation, right? So I know all my oxidation numbers together have to equal 0 because there's no charge associated with that entire molecule or compound. Okay, I know my hydrogens are going to be +1. I know my oxygens are going to be -2 each. Two hydrogens, so 2 times 1, plus carbon is my unknown. I don't have a rule here this for carbon. All right, so I'm making that x because we like to use x's in algebra, right? And then I have 3 oxygens, each at a -2. So that's the 3 oxygens times a -2. All of that's going to equal to 0. All right, so I'm going to simplify this down. 2 plus x plus -6 equals 0, right? So I can say x plus -4 equals 0, x equals +4. All right, basic algebra there. You guys see what I did? So I just simplified that down. That's 6th grade math, right? We could probably figure that out when you're in 6th grade. Okay. Now, just the math side. We do have to obviously take a look at this compound. I'm not saying that 6th graders can do chemistry. All right. Some of them can. Smart kids. All right. But what we do have here is a compound. We've got 2 hydrogens, 1 carbon, 3 oxygens. Hydrogens are +1, oxygens -2. We don't know our oxidation number for carbon automatically. It's not a gimme like these guys are over here. All right. So all we do is plug and chug until we get our value for X. So in this case, my oxidation number for carbon is +4. All right, see how that works? So again, we take our easy to assign oxidation numbers, we use those to then calculate those that are not so easy to assign. Simple enough. All right, I'm going to erase this mess here so I can tackle the next one, which is slightly more complicated. All right, so I'm just going to get rid of the chat there. All right, so I've got sort of obscure compound here. So I've got a zinc attached to 4 hydroxides, and my overall charge there is -2. All right, so what I'm going to do is I'm going to again use algebra with my knowns to calculate the value for zinc. All right, so again, I know oxygen is going to be -2. I know hydrogen's +1. Okay, so zinc then would be my X. Right? I don't know the value automatically for zinc. So this time, my algebra equation is going to have to be equal to -2. All right, so I'm going to say X plus, okay, 4 times -2 plus 4 times +1, or 4 times 1, excuse me. All right, yeah, see what I did there? So the 4 distributes to everything inside the parentheses, just like it would in math, right? So I have 4 hydrogens, 4 times 1, 4 oxygens, 4 times -2. Now, because I have this little -2 up there, that whole equation then needs to set itself equal to -2 this time instead of 0. Okay? So we'll simplify. So X plus -8 plus 4 equals -2. X plus 4 equals -2. Sorry, -4, right? X equals 2. Right? So my value for zinc there is +2. Simple as that, okay? Now, practice that. Practice, practice, practice. That, being able to assign your oxidation numbers is fundamental in being able to also then write your redox half reactions or identifying when the reaction is redox in the first place. All right? All right, now moving forward, okay, we're going to take a look at a reaction. Okay, so I'm making some assumptions, first of all, that at this point you know how to balance things. Okay, so I have an unbalanced reaction here. So I'm going to go ahead and do that real quick. Always, always, always make sure your reaction's balanced first. All right, so I see I got 2 chlorines there, 1 there, so I'm going to put 2 there, 2 bromines, 2 there. That balances me out. I'm not going to spend time talking about that. If you're trying to do redox equations, you ought to know how to balance things already. All right, now, what am I going to do here to identify this as a redox reaction, first of all, and then, if it is, write my corresponding half reactions, okay, which involves an electron transfer. All right, so, like I said before, the fundamental skill is being able to go and assign oxidation numbers to everything in the reaction first, okay? So, I had a couple rules. First of all, if it's elemental, the oxidation number is 0. So we're going to look up here first. Is there anything in its elemental form? Hint, 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 hint. Yeah, chlorine is not attached to anything. It's not in an aqueous solution. That's just chlorine gas, right? So I'm just going to write a little 0 above that. Boom. All right. On the right side of the equation, my bromine, right, which is actually one of the 2 elements. It's a liquid, but so, all right. Also in its elemental form, that's going to be 0. Okay, now, what I have here are 2 ionic compounds, sodium bromide and sodium chloride. All right, ions, right, you just take the charge. And again, if you're this far into chemistry, you ought to know the charge of your ions at this point, right? So sodium, being a metal in group 1, is a +1, right? Also over here, +1. Bromine is a halide. Halides are -1, chlorine over here, -1. All right, so in that case, We didn't have to use hydrogen and oxygen to figure it out. We just took the fact that those are ionic compounds, and we know the charge of sodium and bromine, because your chemistry teacher taught you that at some point, okay? So there we go. We have our oxidation numbers assigned. So how do we tell if it's a redox reaction? What we do is we look to see if anything with an oxidation number up here changed from the left to the right. Is there change from the left to the right? So sodium, right here, +1, +1, no change there. Bromine goes from a -1 to 0. Ding dong, there's a change in oxidation number, right? Now, whenever one changes, that typically means another, something changes. Chlorine goes from 0 to a -1. All right, so is this a redox reaction? The answer is yes, because some of the elements change their oxidation number from the left to the right. So it is a redox reaction. So when that's the case, your teacher, this guy, right, is probably going to ask you to do your half reactions. All right, so with our half reactions, we do not need to include those that are not part of the redox reaction. And redox is an electron transfer, right? So all we're going to do is we're going to show where the electrons came from and where they went to. All right, so we have two halves. We have our oxidation, and we have our reduction. Boom, boom. Now, in that, what we have to be able to do is identify what is oxidized and what's reduced. Now, there's a little helpful tool, right? Oil rig. All right. Now, what that does is it's a little mnemonic device. So oil stands for oxidation is loss of electrons. Rig is reduction is gain. So what we're looking for our oxidation half is which element lost electrons during this reaction. Okay. And so if we're looking up here, in the case of here, we're going to look for loss of electrons as an increase in our oxidation number. Okay, that sounds confusing. Electrons have a negative charge, so if you lose electrons, you're going to increase your charge over time. So let's look from the left side to the right side. So sodium goes from a +1 to a +1. There's no change there. So that kind of tells you actually sodium's not involved in this. Bromine goes from -1 to 0. Is that an increase in oxidation number? Correct answer is yes. That is, right? Going from -1 to 0 is an increase in your oxidation number. So that is the oxidation half. All right, so the way that looks is I have two bromines on the left side, so the red. 2 Br minus. Okay, now on the left side of my arrow, we'll write Br2 liquid. Okay, now what has to happen for that to occur? All right, so in order to be oxidized, we're saying that oxidation is loss of electrons. And the way we write that, okay, is on this side, bromine is in its elemental form, right? So these two bromine ions became that bromine molecule, all right? And then in doing so, 2 electrons were lost there, okay? So how do I know that's 2 electrons? Quick way to check that. What's my change in oxidation number? It goes from a -1 to 0. So it's a change of 1, right? There's 2 of those, 2 electrons. That's where that 2 electron came from, all right? Now, my reduction half of this reaction then is, reduction is gaining electrons. We're going to look for something that reduced its charge. So reduction, reduced oxidation number. All right? So my chlorine in this case goes from a 0 to a -1. That's a reduction. All right? So on this side of the equation, I have Cl2 gas, right, which has an oxidation number of 0. On my right side of my arrow, it is 2Cl minus, because that 2 goes for both the sodium and the chlorine. All right? Now, if it's an ion on this side, it had to gain electrons during that reaction. So 2E minus, right? And again, that 2 comes from the fact that I have a change of 1, but there's 2 of them, 2 times 1, 2 electrons. What should also happen when you guys do this, that number in your oxidation should be equal to the number in your reduction for electrons, right? So just like we balance things, because we have to have conservation of matter, we're going to balance our electrons out in our 2 half reactions. These 2 electrons are actually the same 2 electrons. So what to consider here is the bromine ions, 2 bromine ions got rid of 1 electron each, or 2 electrons total, right? And transferred those to 2 chlorine atoms to make chlorine ions. Transfer of those electrons, which we mapped out in our 2 half reactions. And that's typically what we're going to be asking you to do with an oxidation and reduction reaction. All right? Now, that one, relatively simple. Okay, I know that's a lot of steps, but it is still relatively simple. All right? We'll do one that's maybe slightly more complex. All right, down here. So here I have iron oxide, which you guys would know as rust. Okay, and carbon monoxide gas reacting to give me just pure iron metal, so elemental iron in that case, and carbon dioxide gas. All right, so we'll probably ought to balance this one guy first. All right, so if we go through and do our balancing, I see I've got 4 oxygens on this side, 2 on that side. All right, so I'm gonna have to make this a 3 and this a 3, right? That gives me 6 oxygens, 3 carbons, 2 irons. I'm gonna need a 2 there. Balanced. Okay? And again, I'm assuming you guys know how to do that by now. All right, but anyways, so that is now balanced. Let's go through and do our oxidation numbers. All right? So, what do we have that's our gimme? Do we have any elements in their elemental form? We do. Let's go ahead and write our 0 up there. That's our easy one. All right. So our next gimmies are hydrogen and oxygen. I don't have hydrogen involved in any of this, but I do have an oxygen here, and the oxygen is not elemental. It's attached to something in both those cases. I'm going to assume that's a -2, that's a -2, that's a -2. All right. So, therefore, right, we need to go back and infer our iron oxidation numbers and our carbon oxidation numbers. Okay, so I've got 3 oxygens at a -6, right? There's no charge attached to this atomic or ionic compound. All right, so that means the iron side needs to be +6. Okay, so if that's a -6 +6, there's 2 irons, that makes that a +3. Okay, now I'm doing the oxidation numbers a little faster now because we already had that little lesson on that. Okay, here I've got carbon monoxide. We're saying that it's neutral, so 1 oxygen, 1 carbon, so this is a -2. That must be a +2. Okay, and here we got iron with charge of 0. Over here I've got carbon dioxide. So this side is -4. That must mean that this carbon is a +4. Okay? So again, I hope that you're starting to see just how important accurately putting your oxidation numbers is and being able to do this process. All right? So what we're going to look for again is this a redox reaction? Do any of the elements change their oxidation number? And it should be pretty obvious that iron changes and carbon changes, whereas oxygen stays the same. Now, that is not to say that oxygen is not part of this reaction. It's just not part of the electron transfer. Okay? So, again, with our oxidation and reduction half reactions, we're zeroing in, we're focusing in solely on where the electron transfer occurs. What loses electrons, what gains, and that should be the same number of electrons in both half reactions. All right? So again, oxidation. Okay, so remember, oxidation is loss, right? So for oxidation, we're looking for something that loses electrons, and the way we recognize that is because electrons are negative. If we lose electrons, our oxidation number increases. does anything increase its oxidation number from the left side to the right side? And I'm pointing to it. Carbon goes from a +2 to a +4. All right? So here's how I'm going to write this. I have 3 carbon atoms on this side. I'm going to write 3C2+. Okay? And then on this side of the reaction, I have 3C4+. All right? So how many electrons are needed to make that change in oxidation number? All right? My oxidation number changes by 2. Right? So I go from a +2 to a +4, right? So that's a change of 2, but that happens to 3 carbon atoms, or carbon ions, kind of in this case, okay? So all I'm going to do to figure out my number of electrons is I'm going to multiply my change in oxidation number times the coefficient. So my change is 2 times 3, that's 6 electrons involved in that. So again, my change in oxidation is a 2, right? That happens to 3 atoms, so 3 times 2, 6 electrons, all right? So in my oxidation step, I'm showing that these 3 carbons with an oxidation of +2 become these 3 carbons with an oxidation of +4, and in doing so are separating 6 electrons from them. Okay? Now in reality, these electrons are transferred from the carbon to whatever is reduced. So my reduction occurs here. Right? So notice oxygen stays a -2 on both sides. Again, we can eliminate that from our half reactions. Not that it's not part of the reaction in this case, it's just eliminated in our half reactions. All right? So my iron goes from a +3 to 0. That is a reduction in oxidation number. All right? So on this side, I have 2Fe3+. All right? Okay, on my right side, I just have 2Fe solid. All right, so in order to make that happen, what had to occur? It had to gain electrons. That's what happens during the reduction. All right, so how many electrons is it? It should be the same as this number, but let's double check. I've got a change in oxidation of 3, right? My coefficient is 2. What's 3 times 2? 6 electrons. All right. Now, a couple things to notice. During oxidation, the electrons are written on the right side of the arrow. During reduction, the electrons are written on the reactant side of the arrow. Okay? We're just showing that these things combine to make those. Okay? And here we're showing that this had electrons separate from it to make those 2. All right? Now, hopefully this is setting you guys on the path to success with your redox reactions. Now, some of them get a little tougher. Fundamental, balanced molecular equation with accurately assigned oxidation numbers, right? With that just comes a little practice, right? We recognize a redox reaction when we see a change in oxidation numbers for some of our elements, all right? Okay. When there is a change, we can then write our oxidation and reduction half reactions, which shows what's actually going on with our electrons. All right, so in the case of this one, the bromine ions donate 2 electrons to the chlorine gas to make chlorine ions, right? Now, these numbers should match, okay, in your half reactions. So just like we have conservation of matter, when we're balancing reactions, when we write our half reactions, we've got to make sure that our electrons balance in that 2 half reactions, okay? Because that is an actual direct transfer of those 6 electrons to the iron, okay? That's a wrap, all right? Hopefully this gets you guys on the right track.